Lesson: Addressing Limitations in AI Understanding. Addressing limitations in AI understanding is pivotal for professionals aiming to harness the full potential of artificial intelligence in their respective fields. As AI systems become more integrated into various sectors, understanding their constraints and how to overcome them becomes crucial. This lesson provides actionable insights, practical tools, and frameworks that professionals can directly implement to address these limitations and enhance their proficiency. One fundamental limitation of AI is its dependency on data quality and quantity. AI systems, particularly those leveraging machine learning, require vast amounts of accurate, high-quality data to function effectively. Poor quality data can lead to biased, unreliable, or even dangerous outputs. To tackle this, data preprocessing techniques such as data cleaning, normalization, and augmentation are essential. Data cleaning involves removing inaccuracies and inconsistencies, while normalization adjusts the data to a standard scale, thus improving the model's performance. Data augmentation, on the other hand, increases the diversity of training data without collecting new data, which is particularly useful in fields like computer vision. These pre-processing steps ensure the AI model is trained on a dataset that truly represents the problem space. Moreover, the implementation of frameworks like CRISP-DM can be beneficial. This framework provides a structured approach to data mining, guiding professionals from the initial understanding of the business problem through data preparation, modeling, evaluation, and deployment. By following such a framework, AI practitioners can systematically address data-related challenges, ensuring that the models built are robust and reliable. Another significant limitation is the explainability and interpretability of AI models, especially those based on deep learning. These models often operate as black boxes, providing little insight into how they arrive at specific decisions. This opacity can be problematic in sectors such as healthcare or finance, where understanding the rationale behind a decision is crucial. To mitigate this, tools like LIME and SHAPE can be employed. LIME explains the predictions of any classifier in an interpretable and faithful manner by approximating it locally with an interpretable model. SHAPE, on the other hand, provides a unified measure of feature importance by computing the contribution of each feature to the prediction. By utilizing these tools, professionals can gain insights into the model's decision-making process, enhancing trust and enabling better governance of AI applications. A practical application of these tools can be seen in a case study involving a healthcare provider using an AI model to predict patient readmissions. Initially, the model demonstrated high accuracy but lacked transparency, raising concerns among medical professionals. By integrating SHAPE, the provider was able to identify the most influential factors affecting the model's predictions, such as age and previous hospital visits, thus improving the model's acceptance and trustworthiness among healthcare staff. AI systems also face limitations in generalizing knowledge across different domains. Transfer learning, a technique where a model developed for a particular task is reused as the starting point for a model on a second task, addresses this issue. This approach is particularly effective when there is a scarcity of labeled data in the target domain. For instance, in the field of natural language processing, pre-trained models like BERT have revolutionized the way tasks are approached by allowing models to apply knowledge gained from one language processing task to another. By leveraging transfer learning, AI professionals can develop models that perform effectively even in domains where data is limited or expensive to acquire. Another framework worth mentioning is the Model Risk Management Framework, which provides a structured approach to managing the risks associated with the deployment of AI models. This framework emphasizes the importance of continuous monitoring and validation of AI systems to ensure they perform as expected in real-world conditions. By implementing MRM, organizations can proactively identify potential issues and mitigate risks before they impact operations. Furthermore, AI systems often struggle with the dynamic nature of real-world environments. Models trained on static datasets may not adapt well to changes over time. This limitation can be addressed through continuous learning or online learning methods, which enable models to update their knowledge as new data becomes available. This approach is particularly valuable in applications like fraud detection, where patterns of fraudulent behavior continuously evolve. By adopting continuous learning strategies, AI systems remain relevant and effective over time, adapting to new trends and anomalies as they arise. The integration of AI ethics into the development and deployment of AI systems is also crucial in addressing limitations associated with ethical considerations and societal impacts. Frameworks like the AI ethics guidelines from the European Commission provide a foundation for developing AI systems that are transparent, accountable, and aligned with human values. These guidelines stress the importance of involving stakeholders in the AI development process to ensure that diverse perspectives are considered and ethical risks are mitigated. A real-world example of ethical considerations in AI can be seen in the deployment of facial recognition technology for security purposes. Concerns about privacy and potential biases have led to calls for stricter regulation and oversight. By adhering to ethical guidelines and incorporating privacy-preserving techniques, such as differential privacy, organizations can address these issues and develop AI systems that respect individual rights and freedoms. In conclusion, addressing limitations in AI understanding requires a multifaceted approach that combines data preprocessing, model interpretability, transfer learning, risk management, continuous learning, and ethical considerations. By leveraging practical tools and frameworks like CRISP-DM, LIME, SHAP, and MRM, professionals can enhance their ability to develop and deploy AI systems that are robust, transparent, and adaptable. The integration of these strategies not only improves the performance of AI models, but also fosters trust among stakeholders, paving the way for the responsible and effective use of artificial intelligence across various domains. As AI continues to evolve, staying informed about the latest advancements and best practices remains essential for professionals seeking to overcome the challenges associated with AI understanding and utilization.